Does that look right to everybody? Okay, awesome.
That looks perfect.
So my name is Jeffrey Clary. I'm with the Foundation for California Community Colleges, and we'll be closing out with a session on this execution of electrification, in particular, getting the perspectives from some vendors and consultants. And we have a great lineup that I will be introducing in just a moment. I do want to thank Ben and the team at the Energy and Efficiency Institute, however, for thinking about the community colleges as part of this conversation, because one thing that is like really clear when you start actually looking about what are the ways in which you roll out a massive transition at statewide or nationwide scale, the actual components you need in place to make that happen in a large measure are going to depend on our community colleges. So I appreciate the ability to make that link with the work that everybody else is doing. So our logistics are, I think, similar to what you've seen before already today. We're going to have three presentations. We're going to have some time for question and answer after that. So please continue using the Q&A box. I've already seen a lot of action going on there, and interact with your peers to the extent that you're finding ways to connect. So before I turn it over to my colleagues, I do want to say just a few words about what I think the important roles of community college in electrification and more generally in climate work are, because I do think having both people in the private sector, people from agencies, and people from the other segments of higher education, kind of knowing what the particular things we do and how they differ from what everybody else is doing can be really great when you're trying to match up and put together projects in ways that are going to be successful. So I work for the Foundation for California Community Colleges, which is the official nonprofit that supports and enhances the work of the 116 college network in California. So I do think the opportunity for what community colleges can do in electrification and climate more generally is really big and somewhat underappreciated. So we have a huge physical and operational footprint. As I mentioned, 116 colleges just in California. We have deep community ties because community colleges are locally governed and organized. They've got local boards of trustees. They're tapped into city councils and county supervisors, in addition to all the kind of CBOs that are operating at the local level. And just as part and parcel of what they do, they have a huge role in workforce development. So in particular, career and technical education, those kinds of things, those kinds of workers that are going to be like actually doing things on the ground to get electrification happening. So with all of these factors in place, I think we really have some unmatched potential to advance transitions at big scale. And we can do that just building on the existing strengths of the community colleges. As I mentioned, there's huge geographic and socioeconomic reach. Nationwide, 1,100 colleges and 12 million students. And remember, these are basically almost in almost all cases open access institutions, so they can truly reflect like the diversity of their local communities. And part of that allows us kind of a special tool that here in California we're finding is really useful for agencies and other groups that are trying to like build awareness and roll out programs at the local level. So for example, building awareness and interest in various electrification initiatives. You can use colleges in those communities as kind of anchor institutions into which you can kind of funnel information, resources, and then use their their network of connections to like get that impact that you're looking for at the local level. And I'd also say that everything is relative, but for higher education, community colleges are relatively nimble. So they have a decent amount of capacity to respond to emerging workforce needs and really get things in place in a way that it's often harder for other higher ed institutions to do. So if you're out there and you're a private sector partner or someone else, and you've got workforce issues and you're wondering like, how do I get the people I already have on staff trained, or how do I make sure that people that are coming up the pipeline are going to actually just end up in the workforce with the kinds of skills that are more generally useful? There's lots of ways you can interact with community colleges and get those conversations going. We have things like contract education, where an employer can actually just pay a college to put a program together and carry out teaching for example, all their staff on some kind of useful subject matter. Or we can go a longer and more embedded route where we actually change curriculum for 4-credit programs that end up leading to associate's degrees or transfer degrees to go to the other four-year institutions around the state or country. So there are lots of ways, if you reach out to your local community college, in particular to their career and technical education dean or their career center, you can find lots of ways to help start the conversation about meeting your workforce needs. And then if we talk about the kinds of work that community colleges can do, I do think for me, there are like four main fields where the existing strengths just really stand out to me. One is the sustainable facilities and operations, again, with that really large footprint serving 12 million students across the nation. Also, that footprint is in a place where it gets a lot of interaction with the public, and so it can also be used to kind of as a teaching tool and to like leverage what you're already doing. Number two, building the workforce for climate-ready careers. Again, this is just like all those things that we need to make the energy transformation happen. A lot of these programs are where those people can get trained. And then third, I don't want to forget this ability of colleges to act as assets to communities, these anchor institutions in places both urban and rural, ways to get knowledge into communities as well as like services. So for example, a microgrid at a local college can be an emergency response center during a red flag day, or when you have evacuations, as very often happens in many of our rural communities. Our colleges are already stepping in to do this kind of like a community support role. And then finally, places like the foundation can help in the resource development to roll these programs out at the statewide level. So I will just say, I'll wrap up here and pass it on to our speakers, but we are aiming big with our colleges. We have a brand new chancellor, Dr. Sonia Christian, who started just a few months ago. Climate is at the top of her list of priorities for what she wants to be happening at the campuses across the state. She's asking us to think big and work in partnership with all the kinds of people that are represented on this webinar today. Do things like get microgrids growing at campuses across the state, make sure that charging infrastructure is in place and serving communities, especially in communities where that infrastructure is having a hard time taking hold, and using resources like the foundation to access big pots of federal funding, such as the IRA funds that are kind of coming down in different ways to the states now and in the next couple of years. So there's lots of successful models for working with community colleges, and I really hope you'll reach out to your local community college or us at the foundation or people in the chancellor's office if you think there might be a way to help you do the work that you're trying to do. So with that, I will try to stop the share and move on to our speakers. So our first speaker today is going to be Miles Hayes. So Miles is part of the Colorado engineering team at Michaels Energy, where he serves as the lead engineer for the Denver Commercial and Multifamily Electrification Program. He balances his time between technical engineering and providing recommendations and interactions with customers. Miles coaches customers to pinpoint core problems and identify solutions. He focuses on communication between teams to ensure quality deliverables to clients. So with that, I am excited to learn from the first of our vendor and consultant speakers. Miles?
Thank you. Thank you. Can you hear me all right?
Yep.
Everybody. All right. Thank you, Tierney. Get my screen to share here. Okay. Let me know when you can see that. Good to go. All right. Yeah. Thank you, everyone. Thank you, Tierney. Good to see you again. Tierney and I had the pleasure of working with Tierney a little bit on this program a couple months ago. Yeah, I'm Miles Hayes. I'm a senior engineer with Michaels Energy, and we've been hired by the city of Denver to design and roll out Denver's commercial and multifamily electrification programs. So I'm going to talk a little bit today. It's kind of we're early on in the program, so I don't have a ton of great data, but I just want to share kind of how we've scaled it. I think that's the major takeaway I'd like you to see today is how we're scaling our electrification feasibility sort of audits in sort of an innovative way. So I'm going to talk a little bit about the code changes, the program at a high level. I'll go through that pretty quick, and then I'll get down to some of the lessons that we've begun to gather from the field. Again, we've just started kind of surveying our contractors. And so I did some calling this last few weeks, trying to get a few more answers than we had in our survey so far, because we're very early on in the survey process. But we've seen some good engagement. and we've also learned some lessons along the way. So similar to some of the other cities and folks that have presented today, Denver has determined that 64% of its greenhouse gas emissions are coming from its commercial, multifamily, and residential buildings. Our program focuses specifically on the commercial and multifamily buildings, which are accounting for just about half of the greenhouse gas emissions in Denver. And Denver has some ongoing targets. So by 2040, we'd like to cut our emissions, which is a pretty aggressive goal. But all new buildings and homes are going to be net zero by 2030 for new construction. And all existing buildings, we have a target of meeting the net zero energy guideline by 2040. And coupled with that, Xcel Energy, our utility provider here, they're actually surpassing their target to produce 80% of their electricity through renewable energy by 2030. And they're on track to meet their 100% renewable generation by 2050. And so Denver, to accomplish this, organized the Energized Denver Task Force in 2021, I believe. And the task force came out with a list of recommendations. The bread and butter of which were basically to pass a climate tax, which is the Climate Protection Fund. And we're now using just over half of that to go directly towards building owners to help electrifying their systems. The rebates, we have a pilot program, we have equipment rebate programs right now that are live and active. And then we also have what's called the EFR rebate, which I'll kind of get to once you understand what the EFR is. So here are some of the permitting and code changes that have already taken place and are actively rolling out. In 2023, if you pull a permit for a unitary system, so anything that's like a gas furnace, water heaters, smaller systems, if you pull a permit, you have a few different options to choose from to get your permit, one of which is to use this electrification feasibility report, which I'll detail here in the next slide. But in 2025, so right now we're just requiring that you use the EFR as part of the permitting process, but they're not actually enforcing electrification yet. But in 2025, the results of the EFR will actually dictate whether or not you have to electrify that system. And we are allowing for gas backup in some scenarios. So that's kind of an important task, just because we're kind of in a colder climate. We want to make sure that folks are comfortable. But so far, we've seen some pretty good results just from our smaller unitary systems. And then in 2027, we will roll out the EFR for larger hydronic systems. So currently our pilot, we are taking in like boiler systems. As many of you are aware, there aren't fantastic solutions yet available on the market. Hopefully we have some major breakthroughs in our refrigeration technology, but anyhow, in 2027, the results of the EFR will also dictate how much of the hydronic system needs to be electrified. So we'll allow for like partial electrification and other scenarios that I can talk about here in a minute. Okay, so what is the EFR? The EFR is the Electrification Feasibility Report. So Michael's put this together for Denver. And I think I want to make it clear that the challenge that we were faced with from Michael's perspective, the sub challenge, I should say, to the overall electrification transformation has been, how can we first assess and target the most cost-effective opportunities for electrification and make sure that those tax dollars are being spent effectively to electrify the greatest opportunities for greenhouse gas emissions. And so rather than sending engineers on site and performing ASHRAE level 2 audits and and having a sort of an industry standard approach, what we did was we developed this EFR, and it's a tool. It used to be an Excel spreadsheet, which was very clunky, but we've since developed it. It's in QuickBase now. So it's a QuickBase tool, and it's very user friendly, and it asks very simple questions. So now we've trained several contractors to use this. So we've got HVAC technicians, electricians, plumbers, and we put them through a training process. But it's a QuickBase tool, and then it communicates. There's a Python script that runs a model in Python in the cloud. So it uses AWS to engage between the two, and then it spits out this report, this EFR report, which is now required for permitting. So the permitting office takes this report, and then again in 2025, that will determine whether or not you have to electrify the piece of equipment. And basically, it's just looking at overall cost effectiveness, which Denver has put together their own sort of cost effectiveness model. And, we're treating it as a screening tool. It is an energy model, but as many of you likely know, it's very challenging to make an energy model that applies to all scenarios. So we've done the best we could here to basically give us the 30,000 foot estimate on whether or not a system is going to be cost effective or not to replace, and some ideas to what the energy bill might look like. So to date, we've trained over 200 HVAC technicians, again, electricians, engineer. We have a couple engineering design firms that are working with our contracting folks. One of the challenging things about our program is that it rolled out at the same time as these permitting changes. And some of the permitting changes, we did away with quick permitting for unitary systems, which has been a bit of a headache because now you need to get PE stamped MEP drawings for basically any unitary system when previously you could pull a quick permit. So now that's an extra hoop that our folks have to jump through. But we've tried to keep a temperature of the overall, and I'll show you the survey results. Really what we're at today is we're trying to focus on getting these contractors trained on what is a heat pump, how well does it work, what technology, how has the technology changed and evolved over the last 5 years, because the 90s sort of left a bad taste in their mouth as far as how heat pumps can perform, especially in colder climates. And so in our pilot program, we've got 50 active buildings. Those range from, you can see that the pie chart down below represents the different equipment, the existing equipment that each of those buildings are currently utilizing that'll be replaced. And then we've had to date 127 completed EFR projects, and then 110 that are currently in process. So we're very busy, and all of those come across my desk. So I'm juggling lots of addresses in my brain. So this is kind of what the results page looks like. It's very simple. We've kind of, it's transformed a bit over the year, or over the last year or so, but more or less, we're just trying to show the like-for-like cost comparison between, if you're going to do a furnace, what are the design, permitting, equipment costs? How does that break down compared to the electric alternative? And then it runs a model to estimate the greenhouse gas. The tons reduced. We have a value in there for the social cost of carbon, and then the overall cost parity. Let's see, a couple things to point out here. We've had a ton of rooftop units come through, and the greater majority of those have been dual fuel units because, again, contractors aren't quite sure how to right size equipment, and nobody wants to be sort of the first guinea pig. Again, our city, we're not quite at the California level yet, but we also are competing with the climate here. And then we've had several systems, smaller cold climate heat pumps and mini splits. So in addition to, like I mentioned, we have a pilot program, and then we also have our equipment rebate programs, which just rolled out maybe August or September. And I don't know if I covered this on the other slide, but we're taking over half of our funding towards our equity priority buildings. And so these rebates are actually doubled for our equity priority folks. And you can see that the nice thing about our rebates here is that Xcel Energy is actually rolling out some of their fuel switching rebates. And so we're able to stack these on top of those, in addition to IRA tax credits and the other funding channels. And these, again, are being updated on sort of an ongoing basis. I would say biannual, if I had to guess, but I don't think there's any hard date for the updates. But basically, as we learn more from our pilot program, the goal of the pilot program is to figure out, can we cover the cost difference between the like-for-like gas system and the proposed electrification option? Because really what we want to do is make it so that our building owners, first, we're well informed as to how these systems perform throughout the pilot, but then we also want to target the incentive so that it can cover that cost, that incremental cost, so that you're not going to be burdened by electrifying the system. And then hopefully, and so far, fingers crossed, it looks like utility bills are coming back somewhere close to cost parity. So sometimes a little more expensive. Again, these things depend on building envelope and other parameters that we'll get into. So our timeline for the program sort of looks like this. We've learned a lot. It was very slow going at first. We had a huge learning curve, just getting contractors and building owners aware of the program, helping them understand how to use the tool. Again, we started with an Excel spreadsheet, so some of this data was kind of skewed because a lot of folks don't use Excel on a day-to-day basis, luckily for them. But we've we basically right now today we're sort of in the middle of kind of this blue stage where we're starting to receive a lot of the bids and invoices. We've had a few projects actually come through to fruition, and now the systems are operating, which is exciting. So I get to kind of go out into the field and see, I get to meet a lot of happy business owners, which is pretty exciting. But again, these times, these milestones sort of range broadly depending on the type of equipment that we're looking at. And I'll mention again that today it's been pretty heavily geared towards the unitary systems. And I've only just recently started to get some of the boiler projects coming through the pipeline, which I'm sure I'll have questions about. I've got a million questions for you guys on that. So yeah, so this is kind of our average cost. And again, I wanted to put together a little bit more data than this, but we've seen a tremendous number of cold climate heat pumps come through the program and rooftop units. And sort of the average total project cost for the cold climate systems has been right in that $15,000 to $20,000 range. And our average rebate that we're giving out is right around $5,000. So if you compare that to the $9,000 to $12,000, $9,000 to $13,000 for the gas like for like, we're winning. We're successfully rolling out heat pumps for at or lower than the like for like comparison, and that's really the goal of our program. It's not an energy efficiency program; it's an electrification program. So I'm going to get into some of these lessons from the field. I think I'll get through these pretty quick, so we'll have some extra time for questions. But I guess what I really wanted the takeaway to be is less about maybe the questions and answers that we've been performing with our contractors, and it's been more about like measuring the disposition. Because at first there was a lot of resistance to the program, a lot of contractors that they've been in the field for 15, 20 years, and they are comfortable. They're resistant to change, and so we had to really show this as a business opportunity. And I want to mention that Denver has this EFR rebate program. So in order to get the EFR done, if you pull a permit for a furnace today, one of your options, and in 2025 you'll be required, is to perform an EFR for every single furnace, every single rooftop unit, water heater. So you can understand that that's quite the workload, and it's a new workload for our contractors. But we've gotten them, we've managed to get them excited about the business opportunity because we're actually paying for each of those EFRs to be completed, and we could pay up to a $2,500 cap, which is insane considering it just takes a couple hours. You go on site, you populate a few fields into our tool, you send it to me, I run the model, and it spits out a page. So it's really a good business opportunity for our contractors, and they're starting to see that. And what it's done is it's getting some of our minority-owned smaller businesses. We've really focused on training those folks, and we've been able to successfully get them into new market, into new buildings that otherwise they wouldn't have maybe had a foothold in. And so they see it as a really exciting opportunity and as another cash flow. So it's another tool on their tool belt of services that they can provide. And they don't have to be qualified to provide like an ASHRAE level 2 audit. You don't have to be an engineer to be able to do an EFR, which is really nice. So I really want to focus on the disposition. We've been asking these questions. They're sort of high level questions right now, because again, we're kind of early on in our survey process. But right now we're really trying to gauge the temperature as to whether or not contractors and building owners how are they feeling about the program and what things can be improved. So this first question is really just, have you interacted with us? Have you been engaged? Are you feeling like we have a big marketing team. We're doing a lot of outreach, and we're just really trying to get this huge industry to sort of shift the mindset. And that's been a task in itself. But so far, the general disposition has been positive. You can see there's 13% of the responses were actually detractors, meaning that they didn't have good feelings about the program, which is honestly a lower number than I had anticipated earlier on in the program. So we've seen a pretty good adoption from the mood of contractors. This next one here, what did I say? What's your experience with EFR? What challenges did you face? Did you seek any help from our program? Uh-oh, my headphones are dying. Let's see if I can get through this. Raise your hand, Tierney, if you lose my audio, will you? Okay, thanks. So far, yeah, there haven't been major issues with our program or with the building owners. The big trouble has been, and this has been something we've heard over and over, contractors were already busy, and now they're even more busy. And now permitting is taking a little bit longer. They're having to learn new steps and jump through new hoops. So that's been a little bit of a challenge. We asked what would help you more easily navigate the EFR. And again, this sort of relates to the permitting process, because now you have to get the engineering design work done. And so that is this huge piece of this huge chunk of time that now falls smack in the middle of your system, your project. And so really moving that forward could be, has been a common theme. So we're working through how to, right now, what we're trying to do is get our engineering firms that are involved, getting them to train and hire junior engineering staff. So working with colleges and community colleges and things, getting a junior engineering staff in there to do the initial MEP design work and then have their PE to, sign off on it. And that will allow those junior engineers to also get a couple years under their belt from the, towards their PE. But so we do have several engineering firms that are like actively working to scale up their workforce. And then again, workforce development is going to be a big topic for us. I'll kind of touch on in a minute. Based on your experience or expectations, will existing rebates cover the difference? This is the big unknown, right? The big purpose of the pilot is how much money do we have to pay for what kind of a system and what type of a building to cover the costs, the incremental costs. So if you're doing a rooftop unit, how much more expensive is it to commission and install and purchase a either dual fuel or exclusive, a heat pump rooftop unit? So general responses have been that, yes, it does cover the cost difference for the smaller systems, but we're not quite there with the larger systems. So that's why we're continuing to work through the entire complex system that we're managing to figure out what those price points are. And that's why those rebates are probably going to change in the next year. But right now we're really hitting the head, I think, with the smaller systems. We've had really satisfied building owners. Okay, so what barriers to electrification are you encountering? What barriers do you expect commercial and multifamily building owners to encounter? And this is sort of what I would expect to see. Really we're coming across a lot of just the financial resources, building owners that can't afford to electrify. So we're trying to show them, hey, you're going to have to replace the system anyway. If you wait till 2025, you might not have access to the same. You'll be required to more than, you got the carrot and the hammer, I guess, metaphor. But we're trying to show them, if you replace your rooftop unit, we're going to make it even for you at least. And other barriers has just been, like I said, familiarity to equipment. So not only do the building owners, they may not have ever even heard of a heat pump, but contractors, again, have a resistance to them just because of the way that they used to perform. And there's just a knowledge gap in understanding how the technology has changed. And then the obvious supply chain issues, microchip issues, that's kind of more on the larger system side. I think anything under about 5.4 tons on a rooftop unit, I can usually get within a reasonable amount of time. But we've been working with some of our vendors. We contacted several earlier on in the program to try to work out, move things upstream a little bit so that we can get them to sit on a bit more inventory before we got started. And that's been another challenge because we are not a utility program, we're a municipal program. And so there are a lot of moving pieces as we work with Xcel Energy and we work with the city, and then we try to get, Trane or whoever to scale up their stockpile. And again, with the disposition, this is one that I thought would be more, 50% feel that there are too many barriers, and I would have maybe even guessed that'd be higher. So we're slowly seeing that number come down as we prove our case. And then a bit from, I guess, an engineer's perspective, and I've met with a number of our engineering firms. So this is coming from maybe 3 or 4 folks that have been very involved with the pilot now for a year or so. Upfront costs. So a lot of these opinions really align with what we're seeing from our contractors in the field. But really, I think some of the bigger barriers that were not anticipated are things like right sizing. A lot of the gas systems are oversized. Most of our contractors are right sizing for cooling, and then we're adding gas backup to make up the difference between the cooling and the heating BTUs. And then just installation knowledge, understanding how to properly install, balance, and commission, and then integrate with existing control systems. There's a lot of new nuances when it comes to, let's say, like a heat pump rooftop unit that a lot of our contractors just are not familiar with. And then again, supply chain issues, lead times, and then heat pump performance. That's been a big concern. There's a lot of material out there that questions how well a heat pump can perform in colder climates, and nobody wants to again be sort of the guinea pig. But I think we're at the point now where the research has been done. We've worked closely with the Minnesota Center for Energy and Environment, or Environment and Energy, one or the other, MNCE. And they've got several field studies proving that the systems are working effectively in some of the coldest climates. And so we're really at this point trying to reinforce that, but also make sure that our building owners aren't stuck in the cold. Yeah, and then there's just also a lack of understanding with how to operate a heat pump, understanding that you're not going to get this blast of warm air. You know, it's sort of just it's a big difference from what people are used to, and we've heard a lot about that. And then for the central plant systems, this is something that we're just getting into, and it's something that I'm eager to learn from all of you. So I'll be reaching out, but right now what we're trying to figure out are what are the most effective solutions to electrify fully or partially central heating plants, which is very challenging. I think maybe one of the biggest opportunities that we've come upon has just been decoupling domestic hot water, and then the challenge there is getting our hands on the actual central heat pump, the CO2 systems, for example, the large domestic hot water central systems that you can use for multifamily buildings. That would be if we could streamline that a bit, that'd be a popular solution here. We also have Aquatherm, which is a really weird kind of a unique system. It's like a mini combo system in our apartments here. We have gas water heaters that are passing potable water through fan coils and then to the faucet. So it's this mini boiler system, which has presented sort of an unexpected challenge to electrify, but we've kind of come up with some cool solutions there using air to water systems. Yeah, and then just the upfront costs. Obviously, we're not going with electric resistance boilers. And so how can we partially electrify? We have old radiant systems. We have some building owners who are cutting zones off of their existing loop and then just doing unitary systems for those zones. And then when they replace their boiler, they can turn their boiler down now. And then when they replace their boiler, they can downsize the boiler. And yeah, I guess that's really my presentation. I'm going to open it up for some questions.
Yeah, so actually, I think the order of events is we're going to have all of the panelists present, and then towards the end, we'll save time for Q&A.
That's right.
So thank you, Miles.
Thanks. Yeah, thank you. Let me figure out a quick sharing here.
Thank you, Miles. That was great. It was really interesting to hear the field surveys to actually get some on the ground reports of how people are perceiving some of those changes. So as you formulate your questions for Miles and our other panelists, go ahead and drop them in the chat so that I can make sure that we bring them up once we've cycled through our speakers. But at this point, we will turn to our next guest, Colin Moyer. Mr. Moyer of Affiliated Engineers has advanced project experience in district energy systems with complex requirements. His responsibilities range from utility master planning with life cycle cost analysis to demand side assessment and evaluation, to supply side design and optimization. His central plant design experience ranges from concept design through construction administration, commissioning, and operator training. So, Colin, welcome.
Thanks, Jeff. Hopefully you can hear me and see my screen. Okay, great. I wanted to add to the bio that probably the reason I'm here is I've been working with UC Davis since 2017 on studies and related implementation projects to convert the campus from steam heat to a lower temperature hot water heating system, and then to ultimately generate that hot water with electric heat pumps. And we've been considering some of the technologies that we're going to go through today. The idea for this presentation is just an update on the current status of the market in the United States for the availability of district or campus scale heat recovery chillers. All right, so this slide here is just a little bit more about AEI, who we are. 19 offices across the country, based in the United States, 800 employees, and we have 70 employees dedicated to energy and utilities. So first of all, what is a heat pump? We all have been using that term. I just wanted to get on the same page with everyone on what a heat pump is before we go further into it. So a heat pump is a device that moves heat from a lower temperature source to a higher temperature sink. It requires work to do that. That's opposite the direction of natural heat flow. So you're going to need to put work into this process to achieve that direction of heat flow. The heat source and the heat sink, these can be liquid, solid, or gas substances. They don't need to be the same. Like you could have an air source heat pump that makes hot water. So it's sourcing from air, but it's making a hot water. I'm going to be talking about water to water generally, and and even liquids. It doesn't need to be water, but at the campus scale for heating and cooling, we're generally talking about a water source, which is often chilled water, and then a hot water sink. The cycle to achieve this, some of the more common cycles for heat pumps are vapor compression, absorption, and adsorption. There are some other cycles like the Stirling cycle and maybe some others that I'm not even aware of, but we primarily see vapor compression and some absorption heat pumps. We're going to be talking about vapor compression heat pumps today. And then the work input can be electric, thermal, or mechanical. And what we're going to talk about is mostly agnostic to the work input, although the packaged solutions are typically provided with electric motors. They could be provided with steam turbines if they were customized, or engines, but we're mainly the availability of what we're talking about is an electric motor. So we're going to be using an electric motor to do work input in a vapor compression cycle to move heat from lower temperature water to higher temperature water. This is a simple depiction of a separate heating and cooling system. This is very similar to the existing UC Davis heating and cooling systems where you have fossil fuel combustion is a high grade heat resource that makes steam. I don't know if the top is blocked. Let me try this. Alt Shift H. So UC Davis has a steam distribution system, which is fairly common across universities in the United States and across the world. That is distributed to the buildings, utilized for processes, and then converted to a lower temperature heating hot water. I'd actually jumped a slide there. And then the cooling system is typically a chilled water distribution system that comes back to a chiller. And the chiller is actually a heat pump. That chiller is taking waste heat from the buildings at a colder temperature, and it's raising its temperature so that we can reject it. We usually use evaporative cooling towers in larger systems, but essentially the heat is absorbed from the building using a low temperature medium, which is chilled water. And then the chiller is a heat pump that raises the temperature to above ambient conditions so that we can get that heat outside. So it's called a chiller. It's a heat pump, but we call it a chiller because its main purpose is to chill water. And then we can change that chiller into a heat recovery chiller. This is also a heat pump, but the heat recovery chiller is called such because some of the heat from the chilled water can be recovered for beneficial use in the heating system. The one that's shown here is a type of compound heat pump that can either recover the heat or reject the heat. There are some dedicated heat recovery chillers that can only generate hot water, and there are some that can generate hot water or can reject heat to ambient. So we call this a heat recovery chiller because it's still primarily chilling water for cooling. It's using that as a heat source to recover it, but we call this a heat recovery chiller. And then we also start throwing the word heat pump in there, or water to water heat pump, or district heat pump. And when we do that is when we start to advance to pulling low-grade heat sources that are in excess of the actual campus cooling load. Systems start to look like this. We do have cooling load, and we can do simultaneous heating and cooling very high efficiency because we're displacing work that would have otherwise been done just for chilling. So some of that work is saved. We do a little bit of extra work, and we can make beneficial heating off of a similar unit, go from a chiller to a heat recovery chiller. But there's only so much chilled water demand on campuses during colder weather. And so you get to the point where you've made all the chilled water with your heat recovery chiller, but you have not made all the heating that you need for the system. So this diagram here, which would require a lot more time to explain it in detail, basically shows how you can move different heat sources around, and particularly in the bottom right corner, there's a number of other low-grade heat sources that are available on many campuses that can be connected on to a chilled water system. These are false cooling loads that increase the load on the chilled water system when they're dispatched. You would dispatch them selectively to provide more source to the district heat pump. And then those low-grade heat sources can be converted to useful heating temperatures through the heat pump. And so that's why we use that term heat pump, because it's no longer just a chiller. It is doing some beneficial cooling, and it is chilling water to achieve its intended purpose. But we start to call it a heat pump just because it's really just moving heat from one temperature to another. Where that heat came from may have been a cooling load, or it may have been another source of low-grade heat. Just wanted to get on the same page with some definitions there. We're going to talk more about the heat pumps that are available here. On the left side, we're showing again a compound style of centrifugal heat pump that can either reject heat or recover heat. And then on the right-hand side, we're showing another type of compressor here. It's called a positive displacement heat pump. The image is meant to depict a screw, but there's also scroll and reciprocating type compressors. Due to that type of compressor, they're typically dedicated heat pumps or dedicated heat recovery chillers. They wouldn't have to be, but a compound centrifugal is a good way to handle heat rejection or heat recovery, just because of the multiple stages. So it's a little bit more efficient to reject heat with one of those, but you could also use a positive displacement in the same fashion. And then there's other types of heat pumps that are on this diagram that we're not going to go into in detail, but there are opportunities to cascade into heat pumps that generate steam. But this is putting a lot more work in. You've already done the work to make heating hot water. It requires much more work to convert heating hot water to steam. So while it can be done, it's usually not the best choice. It's a lot more efficient if you can utilize heating hot water. It is a challenge, like at UC Davis, where there's an existing steam distribution system. You don't have a network in which to do central heat pumps distributing hot water to buildings. But that's some of the work that's been going on to put that system into place. And it's being done when the steam system would have needed replacement anyway. So some of the steam system was at the end of its life, and it's being replaced with hot water so that the campus can take advantage of the efficiency gains that you get by generating hot water with a lower temperature heat pump. A little bit about refrigerant, because that's closely related to technologies and has changed a lot recently. So just an update on that. This is a simplified timeline of refrigerants that are available in chillers and heat pumps. And we've recently reached the end of the phase out of the ozone depleting substances per the Montreal Protocol. HCFC 123 was one of the latest refrigerants to reach its phase out date. So new chillers stopped being delivered with 123 in 2020. And more recently, there's been regulations on refrigerants that contribute to global warming. So, refrigerants are classified with their ozone depletion potential and their global warming potential. All of the regulated ozone depletion substances are now beyond their phase out date. So there's not going to be any more chillers in the US that utilize ODS refrigerants. There are still currently producing chillers and heat pumps that utilize higher global warming potential refrigerants. One of the common ones is HFC 134A. It was banned by the EPA under this SNAP, Significant New Alternatives Protocol, which was a program that the EPA had to phase out the ozone depletion refrigerants. Because the EPA used SNAP to attempt to regulate 134A, it ended up being partially vacated by the U.S. Federal Court of Appeals. And following that, California and 7 other states at the time this slide was put together, but I think maybe about a dozen other states decided to actually enact the same regulations that the EPA attempted to put in place and put a ban on any refrigerant with a global warming potential of 750 or above. And that's going into effect at the end of this year. So we're actually, unless your chiller or heat pump is already in manufacturing and nearing completion at this time, for California and the other related states, it's already too late to use a refrigerant with a global warming potential of 750 or above. For the rest of the country that doesn't have state level legislation, recently it was made constitutional by the AIM Act a few years ago for the EPA to regulate refrigerants that have high global warming potential. And then the IRA actually funded the rulemaking process, and the EPA about a year ago issued a draft rule, and just this month has issued the final rule. And there is actually a ban on all refrigerants with a GWP of 700 or above, and that is in effect 1 year later. So it's the end of next year. Given the lead time of chillers and heat pumps in the market right now, lead times are looking at about a year. So if you were looking for a refrigerant with a GWP of 700 or above, it would need to be put on order almost immediately. Pretty soon we can just put all this behind us. There's been a lot of change, but we're like at the end of the possibility of seeing refrigerants with a GWP of 700 or higher. So that means 134A and a lot of other HFC refrigerants are no longer going to be allowed in new chillers. The next generation of refrigerants means that there's a lot of change with equipment availability. So there's HCFO 1233ZD. That's a pure HFO with a global warming potential of 1. So that's going to be a long-term refrigerant option as far as we can tell. HFO 514A is an HFO blend, but it's a blend of 2 HFOs. So it still has a global warming potential of 2. And just in case you're not familiar, for comparison, HFC 134A has a global warming potential of 1,300. So these other refrigerants are like more than 1,000 times less global warming. Next one down is HFO 1234ZE. The first 2 were lower pressure refrigerants, and then HFO 1234ZE is a medium pressure refrigerant. That one also has a global warming potential of 1. It's a pure HFO. Following that is another pure HFO 1234YF. This has been used in the automotive industry. It is getting some negative attention in Europe, and I believe there are some bans on this refrigerant in Europe because of another 3-letter acronym. So we've solved ODP, we've solved GWP. The next acronym is TFA, which is trifluoroacetic acid. And HFO 1234YF apparently breaks down into a high concentration of TFA. So that's sort of the newest concern. And so we don't know the future of that refrigerant, but it hasn't been used in any large chillers or heat pumps yet. But the reason it's introduced is because the next one down, HFO HFC 513A is a blend of an HFO and an HFC. It's 55% YF. It's 45% 134A. So it's actually a blend of something that is already banned and something else that might be banned. So we put a question mark on there. It's not under any current regulations, but we don't know if it's going to be around for 10 to 20 years. There's not any immediate legislation. Now that we know how the EPA has finalized the technology transitions program through the AIM Act and the IRA, they're not regulating it now, but we don't know if they would in the future. And then we also have HFO HFC 515B. And I should mention, the 513A is basically works very similar to 134A. So the good thing about it is all the equipment developed around 134A can utilize 513A today. It's not going to be phased out in the next 1 to 2 years. 10 years from now, we're not sure. That's the good thing about that refrigerant. But the bad thing is the 2 substances that it is, that its major components are. And also its GWP is still relatively high. It's around 600, where the current limitation is 700. These other HFOs are all in the single digits. And then HFO HFC 515B, it's another HFO HFC blend. In this case, the HFO is 1234ZE, so it is a better HFO. It doesn't have the TFA concern, but the HFC is 227EA, which is a highly potent greenhouse gas, much more so than 134A. So that's why we have a question mark there as well. We are unsure of how long that will be a refrigerant choice. That refrigerant was developed because one of the challenges with 1234ZE is that it's mildly flammable. It's classified by ASHRAE 34 as an A2L. There are certain things that you have to do to the refrigeration machinery room to install an A2L refrigerant. They are not nearly the measures that you would have to do to install a highly flammable refrigerant. There's just a few things that have to be added. 515B was developed. It is about, I think, 93% 1234ZE, but they mixed it with a little bit of HFC 227EA, just enough to get that flammability down to ASHRAE 34 class A1. So it eliminates the A2L issues. They're not very big issues. It raises the GWP to about 200. So that's the trade-off you can consider, but they basically work in the same equipment. Below that are some naturals. So there's R744 is CO2, R717 is ammonia, and then there are many hydrocarbons. Those were some of the original refrigerants in use. On the left of the chart, the middle of the chart, we kind of faded it out. They became less common when all these other synthetics were on the market. But then after the Montreal Protocol and then focus on global warming and the Kigali Amendment to the Montreal Protocol and all these next generation refrigerants, we are starting to see the natural refrigerants under consideration more, just because they're proven technology, but they do each have challenges. We're going to talk a little bit more about CO2. Its challenge is that it has a very low critical point. That makes it very unique, and we're going to talk about that. R717 and the hydrocarbons, those are just costs related to safety equipment. That's the main challenge. All right, so there's two types of vapor compression cycles, or at least I'm comparing two that I'm familiar with here, subcritical versus transcritical. So really the only refrigerant that I've seen used in a transcritical cycle is CO2. It has a very low critical point. It goes transcritical in a regular chiller, depending on what type of condenser you would have. It's like 70 to 80 degrees outside, it's going to switch to transcritical. So you can use CO2 as a very efficient vapor compression cycle for lower temperature cascade systems, where you actually you're refrigerating the condenser of the CO2 cycle to maintain it being subcritical. When you go transcritical, there's a lot of challenges and additional costs, but there are some things that can really be helpful in a heat pump. So subcritical cycle on the PV diagram, basically you're evaporating refrigerant, you're compressing it, you're condensing it, you're expanding it. That could be two or three stages. This is showing single stage. The key thing is that in the condenser, we're below the top of the dome. We're actually condensing saturated gas into saturated liquid, and there's no temperature change in that process. So when you have a chiller or a heat pump and that condenser, you're actually heating up a fluid while you're condensing this refrigerant. There's no temperature change on the refrigerant side because it's going it's on the saturation curve, and that means that you don't really care about the entering temperature. You mainly care about the leaving temperature, and that heat exchanger is designed based on the leaving temperature. The compressor is designed for the lift associated with leaving evaporator to leaving condenser, plus the approaches on the heat exchangers. But with a transcritical cycle, the main difference, and the only part that I'm going to get into, is you don't have a condenser because you're not going through the dome here. You have a gas cooler, and then you throttle it in order to change state from gas to liquid. So
Colin, I hate to interrupt. We need to leave time for our last speaker. So if you could get to a concluding slide, we'll make sure that people have access to the rest of your information. But we need to make sure that everybody gets their time. Thanks.
Thanks. So in the gas cooler, there's a large temperature change because we're not a saturated gas to a saturated liquid. Because of the temperature change, it actually there's a large impact on how efficient the process is from entering temperature to leaving temperature. And that's what this chart shows. And that's why you're seeing CO2 used in domestic hot water heating systems that have high range. There's possibilities of COPs in the range of 5. So this chart is hot water supply temperature, which is leaving condenser water temperature, relative to efficiency in terms of COP. So in this case, higher is better. All the dashed lines are CO2. So you can see how CO2 can potentially be much more efficient, but qualified in the legend by color is the amount of differential temperature on the heating system. So it's only more efficient if you have very high differential temperature. If you have normal differential temperature, it's actually less efficient. The remainder of the slides are discussing some equipment, and they're in terms of capacity range and lift. And so you can go through these on your own later on. There's some small high lift equipment available. There's some medium capacity, medium lift screw equipment available. And then you can look into, there's a link there to look more into this new chiller. The York YVWH is a new chiller on the market. There have been a lot of large centrifugals that can only do low lift. There have been large centrifugals like Stanford has that are very large that can do high lift. And then there's 2 other pieces that I wanted to highlight. The York CYK is something we've been considering at UC Davis, and it fills a lot of this void in the middle. Because if you go back here, there's a large area in the middle where a large range of capacity, there's just not high lift equipment. So the York CYK fills that area. And York just announced a small CYK that fills some more of this void. And there's a new product that is just coming onto the market in the past. It's not been announced yet, but I did get permission to share with you that Trane is making a centrifugal heat pump that can do this portion of this operating envelope. So they're going to be announcing that publicly soon, but it's really a game changer in this space. As you can see, it fills up a large part of this diagram.
Sorry, Colin, you mentioned Trane. We actually need to give our speaker from Trane the chance to speak to our audience as well, because we do have a hard cutoff at 2:40. So if you've got maybe one more slide, just wrap things up.
This is it. Yeah, this is my last slide. So I'm just trying to figure out how to stop my share. Don't see how. I was able to take over the sharing, so.
You can cut into 2 of my minutes to share about the Trane chillers.
So, yeah, Kasey, was that Kasey that just spoke?
Yes.
Oh, hi, Kasey. So Kasey Boxleitner is our next speaker, and she's the decarbonization sales leader of the commercial HVAC Americas business for Trane Technologies PLC. In this role, Kasey has responsibility for driving growth in the decarbonization space, and she aids internal efforts to develop and implement standard work practices for strategic growth initiatives while supporting customer efforts to reduce carbon emissions. So happy to have you. And if you need to turn back over to Colin at some point to develop that exciting new announcement, I think we'd all be excited about that too. Kasey?
Thank you. Can everybody see my screen? Good. Okay. Yep. Awesome. So my name is Kasey Boxleitner. I'm the Decarb sales leader for Trane North America, and I'm going to give you guys a little bit of update on the vendor perspective around electrification. What I didn't want to do is turn this into a commercial for Trane, so I'm going to try to talk a little bit about what we're seeing from our customers that maybe any vendor would be seeing, and then kind of give a very brief overview of the type of products available. I'm not going to go into any specifics. So first of all, why Trane as an HVAC vendor, which I'm sure you're all aware, but why we care about what's going on with decarbonization and why we find it valuable to have an entire team and department around decarbonization. It's because we know that 40% of annual global CO2 emissions are generated by the built environment. When we look at the breakdown, it's 27% that comes from building operations. And the rough rule of thumb is about half of your building operations comes from heating and cooling your building. So when we talk about operating HVAC equipment specifically, that's about 13% of annual global CO2 emissions. So as an HVAC equipment vendor, that gives us a really large footprint that we're impacting. So we are really focused on this when we talk about decarbonization. As much as I would love for everybody to want to decarbonize out of the goodness of their hearts, what we're seeing from our customers are these different drivers that are pushing them towards decarbonization. The first one that we look at is like ESG drivers, right? So you've got things like BlackRock or other investment firms that are forcing people or indicating that they want ESG information and valuable ESG data from their customers to make investment decisions. That is like very publicly available through things like CDP, the Carbon Disclosure Project, where you get a grade on your ESG plans. And then you have pushes from the federal government too that our customers are feeling, like the SEC proposed disclosure rules. And then I've heard a couple of people mention, but there is stimulus money available through things like the Inflation Reduction Act, where there is money available for implementing certain types of systems that are decarbonized systems. So that also is pushing people towards decarbonization. Along with those drivers, we also see local policy pushing people to want to decarbonize. So this is another reason why we have people coming to us looking for decarbonized HVAC solutions. I live out in Boston. I'm assuming there's lots of people from California and other cities that are feeling these pressures, right? But we feel pressures too from our local policy pushing us towards decarbonization. As it relates to HVAC, I want to quickly talk about scopes of emissions. Your operational emissions or your scope 1 emissions that are coming directly from your building. So that's burning fossil fuels on site and refrigerants, which I didn't think anybody was going to talk about. But thank you, Colin, you did mention that. And then our scope 2 emissions, right, are our carbon intensive electricity sources. So when we do talk about electrification, we want to be aware of the scope of emissions and not just promote moving emissions from one place to another. We want to be strategic in our electrification as we decarbonize our buildings. That's why I throw in this slide. I often hear decarbonization and electrification being used interchangeably, but obviously they are not. Decarbonizing is reducing emissions, and electrification is utilizing electricity in place of burning fossil fuels. The decarb conversation is bigger around HVAC. So when we talk about decarbonizing buildings, we have what we like to call our 4 pillars of decarbonization. Today, I'm going to focus on electrification of heating because that's the purpose here. But I want to acknowledge the other 3 pillars that we have at Trane, and those are energy efficiency, refrigerant choices, and renewable energy. So I think the first thing that we should do when we talk about decarbonizing our buildings is to look at the energy efficiency of our system and our building. The first thing we want to do overall before we electrify anything is bring our overall load down. It's not just Trane's first pillar of building decarbonization, it's the U.S. Department of Energy's first pillar of decarbonization is energy efficiency. So I want to acknowledge that, as well as refrigerant choices. We just got a lot of information about refrigerant, which is great, so I don't have to go into it, and hopefully that'll leave us some time for questions. But we do think it's important to choose the right refrigerant in your machines as you think about decarbonization and your building footprint. And then finally, renewable energy. As we talk about electrifying, we want to make sure that that electricity is generated cleanly. So when we talk about electrification of heat and the equipment available, that's where Trane, manufacturer of HVAC equipment, has a lot to do. When we talk about comfort space heating, because I do come from Trane Commercial, we're talking about commercial buildings and heating those buildings. 6% of global greenhouse gas emissions come from that comfort space heating. So if we move it onto a dirty grid, like we've said, we are just moving around our emissions, and that's not very helpful. So we obviously want that electricity to be generated using renewables. And so as we move our comfort heating from fossil fuels burning on site to equipment like heat pumps that are running on electricity, and that electricity is generated with these cleaner grids. When we talk about grids, not all grids are created equal. So you can use, the EPA e-grid to look at what's happening with emissions all around the country. And, dark blue is dirtier grids and light blue is cleaner grids. And so when I analyze what's happening with equipment, you could have the exact same equipment operating at the exact same efficiency in 2 different places of the country, and your emissions are going to be different. So it's critical when we talk about our equipment that we know where it's going And we actually get a bigger bang for our buck on efficiency saves when we do efficiency plays in a grid that is less clean. Obviously, we want all of our equipment to be very efficient, but it is important to think about where your equipment is located as well, and also what's happening to your grids as we move into the future. Even if you have a grid where, let's say, burning natural gas is equivalent to using electric equipment because of where the scopes of emissions are, the intent is for grids to get cleaner over time. So the emissions from your equipment would decrease over your equipment's lifetime if you're using electrical equipment. Whereas if you install something like a natural gas boiler, the emissions from that equipment will remain steady for the lifetime of that equipment. As we talk about the US grid, just overall, you can see that the build on the grid over the past couple of years, it is increasingly renewable. It's majority of renewables that we're adding to the US grid. And that gives us a breakdown from 2021 of 20% renewables. And obviously that number is going to increase over time. So our grid is getting cleaner is something to acknowledge. When we talk about electrified equipment, we like to think about it a lot like electric vehicles. The amount of electric vehicles being made is increasing, but because there's so many, regular vehicles on the road, that number is just slowly getting taken over by electric vehicles. We see the same thing with heat pumps. There's 180 million heat pumps that have been installed by 2020. And at the current rate, we'd only have 253 million heat pumps installed by 2030, but we need 600 million to reach the International Energy Agency's net zero scenario. So we need to bring a lot of heat pumps online and a lot of electrified equipment online in order to meet a lot of these net zero goals. With that in mind, there are plenty of states, actually the majority, that have incentives around using electrified equipment in our buildings. So on top of things like the Inflation Reduction Act and federal stimulus money that's trying to enable decarbonized systems, we also have local funding. So depending on where you live, you could look into what is available for you there. Now we can talk about the equipment that's available. We need to be looking at buildings holistically. As an equipment vendor, I think we could get very into the weeds and just say, just pick this one piece of equipment and not look at what's going on with your whole building, but that's not how we're going to achieve strategic electrification in a way that makes the most sense. We need to be analyzing our whole building, mitigating issues, managing the equipment that we put into those buildings to ensure that it is operating the way it's intended to operate. How many of our buildings are actually operating the way they're designed, right? So we need to be very holistic and aware of what's going on in our buildings. With that being said, there are a lot of electrification solutions. There's not a one-size-fits-all approach. The biggest thing that you hear about is heat pumps and chiller heaters. So where traditionally you would use a chiller and you'd make cold water and that was all it did, now your chiller does more. It chills your water, and then instead of just rejecting heat and throwing away that heat, we can utilize that heat and that hot water in our buildings. We have a very cool new system that I'm going to talk about briefly called storage source heat pump, so I won't go into that on this slide, but there's also other systems that you've probably heard of, like VRF, which is variable refrigerant flow. That's an all electric system. We have packaged rooftop heat pumps that you can use. Those even have backup forms of heating, either gas or electric if necessary, depending on the climate that you live in. And then there's even some domestic hot water systems that we have that utilize CO2 as a refrigerant, and they're all electric for generating domestic hot water. This slide goes into a little bit more detail on the types of equipment available, but what I want to point out here is the applied hydronic line. So you can see that you could have, your traditional chiller system where it's cooling only. And Colin talked about this a little bit. So in order to leave time, I will try to go through this very quickly. But then you could have a chiller that utilizes heat recovery. So you're heating while you're cooling. The next step beyond that would be heat pump. So you're heating or cooling, you could be controlling to those temperatures. The next one would be multi-pipe, which is where you are heating and cooling all simultaneously. And then finally is thermal energy storage. And that's what I wanted to talk about when we talk about cool new solutions available. Here we go. So Thermal energy storage utilizes what we're calling a thermal battery. Oftentimes when you think of batteries, I'm sure you're thinking of electric batteries, which are great for electric loads. But actually for thermal loads, what's really great is a thermal battery where you're storing that heat, in our case, by making and melting ice. And so what we're doing is we're helping to decouple the time dependency of your heating and your cooling. And you use that ice along with air source heat pumps and chiller heaters in your building in order to heat and cool your building and use the ice or the water in those tanks to store energy. It is a complex system that would take probably an hour to explain, which I clearly do not have, but it's a really cool new system where we're looking at the whole system and trying to find ways to reduce wasting heat. So we're trying to save that heat for our buildings and heat and cool. And it also allows us to mitigate some of the issues that come with low ambient temperatures and heat pumps. So here's a kind of a diagram of what you would need. You need your thermal energy storage, which are your batteries. So your tanks for your heating and cooling ice, possibly a trickle heater if you're in a very cold climate, and then your chiller heaters and your heat pumps. And it's a really cool system. On top of that, I was also going to mention, we do have our cascading chiller system, which is an engineered to order where we are using centrifugal chillers to get to these really high temperatures, because your heat pumps are often limited by the lift that is available on those units. And so it allows us to bring colder water to hotter temperatures, which is a big gap right now in electrified heating systems. Don't have too much detail on that because, as Colin said, it's very new, but it is a really exciting system that we are doing quite a few designs on and looking forward. People are very excited about it. As a reminder, there are multiple things that you need to consider when you decarbonize your buildings. We are thinking of all of them. Clearly, the rest of the group is as well, because these things were mentioned by others. And I have left us hopefully 5 minutes for questions if we have any. So thank you so much.
Thank you, Kasey. I really appreciate how between the three speakers, we really kind of spanned like the full scale of questions that surround this question of rollout of electrification. So we all the way from like the actual components we're using in refrigeration out to the installation landscape and the regulatory frameworks that set that up, and then what that means at the nationwide level, as you just kind of showed us. So I think really nice coverage of these kinds of issues. So there are a number of questions. People are really interested in some of the refrigerant questions that Colin was bringing up. We won't have time to do all of them, but for example, Bruce asks, how does the refrigerant ban affect the design of systems? In other words, I've heard that replacement refrigerants have lower performance capabilities. Can you give us a quick answer to that?
Yeah, well, 513A systems compared to 134A systems, there's a slight difference. Could be a couple percentage difference in efficiency, so it's not a big impact. And also, if you were looking at 123 legacy type chillers, they operate pretty much the same with either 514A or 1233ZD. So I don't think it's a large difference, but with the new refrigerants, there are some new products being developed that didn't exist before. I think that's the main exciting opportunity, like with 1234ZE heat pumps.
Yeah. So
and with Trane equipment being able to do things that couldn't be done with 123 or hadn't been done yet before that was banned.
Yeah, any efficiency losses through refrigerants, which they're all very similar, we have designed that out. So we ensured that you could still get just as efficient of a chiller with the new refrigerant.
Thanks. Kasey, there's also a couple of questions that just dropped in for you, maybe expanding on the trickle heater concept for colder climates.
Oh, okay. Well, that system is very complicated. I would be happy to share like an application guide with people. But it's just the idea that you might need just a little bit of extra heat in the very cold climates. And so you could have a trickle heater in there. We know some people like their belts and suspenders. But for example, we are utilizing that system, the storage source heat pump system, at our facilities in La Crosse, Wisconsin, where it gets very, very cold and we're not having a trickle heater. So it's not necessary depending on the climate.
Yeah. Another one that I think is for you, Kasey. Do you have industrial grade heat pumps that could capture waste heat from high temperature water and produce low pressure steam?
Ooh, good question. Not available now.
Okay. So while we have maybe a minute or two left, I might ask Miles. You actually explored a lot of how things are being kind of interpreted on the ground and barriers people are running into as they're doing the rollout of these technologies. Is there anything in particular you would kind of single out as like the biggest hurdle? Is it regulatory? Is it workforce? Is it technology at this point?
Yeah, I think, can you hear me okay? I changed microphones. Yeah, I would say all of the above in different ways. I would say definitely regulatory, there's a whole new learning curve, just like I said, with the permitting process here that's causing a lot of sort of kickback. But, I think if you just talk about the easy to electrify stuff, right, quote unquote, I think that the equipment is available, and I think contractors, I hate to say, like, maybe based on their seniority, how long they've been in the industry, it seems like some of the younger folks are like more readily adopting and willing to adopt and push. At the end of the day, they have to make the sale, so we're trying to help them to inform the building owners. So yeah, I would say from the permitting process is a big barrier. Equipment availability for the larger rooftop units, things over, I'd say maybe 5 tons, seem to be farther out, harder to get. And there's the other barrier here is just, I think we're all pretty in tune with grid interactive buildings and thermal energy storage and distributed energy. And I feel like I'm trying to get, you can't shove it all in at once. And I feel like there's a missed opportunity if we're not doing feasibility studies we're looking at electrification, but we're not looking at thermal energy storage opportunities. We're not looking at how can we, optimize things. And so I'm trying to slowly build that into this, even though it's not really the scope of what we're trying to do. But yeah, this has been really insightful.
Yeah, well, thanks to all of you. And there are a couple more questions in that chat box, so I would encourage our panelists to take a look at those and maybe do some individual responses so that people can learn the stuff they're hoping to get from you. And I will pass it at this point back over to our hosts.